Okay, good afternoon, everybody. For this week's Infosys-Chandrasekharan Random Geometry Colloquium, we are actually resuming, I think, after a week or 2 weeks. So we're very glad to have Radhika again. We'll give a talk on Alexander polynomials on the graph map of a torus.
Thank you. I didn't write the title today. Cool. So I want to tell you about Alexander polynomial. So I'll define it in general, but then spend most of the time telling you about a particular formula for Alexander polynomial for mapping torus of a graph map. And we'll do everything through an example. So hopefully, and I guess if you have questions, stop me. Okay. So let's start with this thing can be defined for any finitely presented group. So if I start with a group, then I can write a finite cell complex, or I can start with any finite cell complex, and I let gamma be its fundamental group. I let H be its homology, not torsion. Then I want to consider, so I'm going to just write X tilde. X tilde is usually used for universal cover, but I want this to be the universal free abelian cover. Universal free abelian. So the universal free abelian cover. So it's basically the covering space whose group of deck transformations. So H acts on X tilde by deck transformations. Or basically there is a short exact sequence like this. 0 is fine, right? So this is a universal free abelian cover whose group of deck transformations is this torsion-free homology. Let's fix some point X in X and let X tilde in capital X tilde be the full preimage. So let me define something called an Alexander module. So this is basically this relative homology group. So if I look at the homology of this universal free abelian cover with respect to the whole preimage of X, I should probably put a tilde here, but I'll mostly forget. This is relative homology. And this is a VH module. Because H acts on this X tilde by deck transformations. Okay. So now I have a ZH module and I want to write a presentation for the ZH module. So like imagine this was a group, I want to write a presentation. I want generators and relators. But right now when I say presentation, I mean in terms of a, what is it called, a resolution, like part of a resolution. So I have, okay, so let's say this is generated by n elements as a ZH module. So think of this as the free module generated by its generators. And then it will have some kernel. So if I write the whole kernel here, I will get a short exact sequence. But let me not write the kernel, but just a free module of the rank as many as relators I have. So think of this as relators and think of this as generators. And of course, I can keep continuing, but I only care about this much part. And let's call this map P. And basically, this will be a matrix where the entries will be in like a ZH matrix. And I will call this the presentation matrix. So I will do examples of these things in a while. So I'm starting with a finite cell complex. So as a ZH module, H1 X tilde would be finitely generated. Yes. And I see why is this? That's a good point. Yeah, no, it's not. You're right, it's not obvious. Does it help that I'm doing relative homology? Like it's relative to so the question is, I should say to the Zoom audience, the question is, why is the relators module, why is that a finitely generated free module? Yeah. I'm going to think more about that.
Yeah, essentially the thing is you are allowed to that's the thing. See up to the C power n, there's a compact fundamental domain of this
or because this is a finite cell complex, like that thing X tilde has a compact up to the action of H. Of H, yes. And
so
the two cells or like higher cells are also finite. Yes, thank you. Yeah, it's just coming from the fact that X is a finite cell complex. Yeah, and hopefully when we do examples, this will be more clear. Thank you. Okay, so I have a presentation for this Alexander module, and now I can define the Alexander polynomial. So what's the Alexander polynomial? I look at n minus 1 by n minus 1 minors of this presentation matrix P. Any question? I look at the ideal generated by these minors, and then I take the GCD of all the elements in that set. So if you've heard these words, this ideal here, it's called the first fitting ideal. It's called the first. So I guess one could define, instead of n-1, I could define n minus I by n minus I minors. And I could define like the ith fitting ideal, and I could define like the ith polynomial, but I don't know what those things mean. The first one is called the Alexander polynomial. This probably doesn't mean much, like I've just written some like homological things, but let me say some properties. So so when I say a polynomial, I'm basically, I guess this whole thing will be some element of ZH. Okay. These minors will be this matrix has entries which are in ZH. I do whatever determinant thing, I get some element of ZH, and I take GCD and all that.
So the verification matrix is what it's one by one. Each of these guys, for each of the generators of CH together.
So like, let's say I have a relator R here. Like what do I map it to? So for the right. So I have to choose some generating set here, and I write that relator as, let's say the relator was some word in ABC. So I write like 2a plus 3b plus 5c, something like that.
But then you get this M cross N.
Yes.
And why is it that M should be greater than equal to N? Other one, N minus 1. So that
yes.
It's true for all not.
Yeah, that's also true for the free bicyclic setting, like the mapping torus. That's a good point.
I see. Okay, there is a way of doing this in a silly way. If M is less, then you just put all the others.
Oh yeah, the GCD won't be affected. Like if I throw in extra identities, is that the?
No, that we killed. That's
huh.
it's
Okay.
just that extra nonsense that we put in, just to make it formally. But the GCD is one. It will make sense where M is
bigger than N. Yeah.
I guess the point would be that if your group has divisions, is what
Yeah.
relators exactly equal to N minus 1. Now just one determinant.
But it's not just one determinant, but I have a N minus 1 many. Yeah. So that'll actually show up in like this example we'll do. I'll get one of the determinants to be nice, like what I want, but then I have to prove that all of them are multiples of that. So I was just going to write that this thing is well-defined up to units in ZH. And so yes, this is a fact, which was shown by Crowell and Fox, that this, so right now I started with X, a finite cell complex whose fundamental group was gamma. So let's say I started with a group, finitely presented group. I have my X for that, and then I do this process. But the fact is that this polynomial actually does not depend on the presentation I choose or the X I choose. Does not depend on let's say X. So therefore, you just use the notation delta gamma. And so theoretically, if somebody gives you a finitely presented group, you don't even have to write this finite cell complex or anything. There's something called Fox calculus, using which you can just compute this polynomial. So I'm just going to write Fox calculus here. But I don't know exactly how to use it. Okay. And then, so I should say this polynomial was originally defined for knots. Basically, take the complement of a knot in S3 and like look at its fundamental group. And then I'm basically defining it was originally defined for that group. And there you take X tilde to be the infinite cyclic cover of that knot complement. Then you do this whole business. And just like, so there what happens is like this Alexander polynomial, if it helps you distinguish two knots. The polynomials are different if the knots are different. And there's something called a genus of a knot. So this polynomial also helps you determine genus of a knot. Let me just say that. So this really gives some good information about I guess it can't distinguish mirror images. That's like one thing I said. Is there more that it can't? Is there more stuff that it can't distinguish, like for two knots?
So I think for it, it's
Mirror image. Yeah, mirror it can't.
there's more.
There's more. Okay. Okay. All right.
The point of the polynomial was very distributed more than them.
I see.
So it's important to one cover out, which all of that is starting point.
I see.
It's a completely different dimension.
Cool. So now what I want to do is I want to take a graph map. So this will be my graph map like throughout the rest of the talk. So a graph map. So this is my graph. And it sends vertices to vertices and it sends edges to edge paths, non-degenerate edge paths. The capital letters means I am traversing that edge in the opposite direction. Okay, so like A goes to D inverse, E inverse, and blah, blah, blah. And then through this, I should also write that it's sending this map G is exchanging the vertices V and W. So like A, let's see, A starts at W, but its image starts at D bar, so it starts at V. So W is mapping to V and V to W. That's the map induced on vertices. Okay. So I want to define mapping torus. So now I'm defining a space X for which I will do this computation. So this space is graph cross 0, 1, quotiented out by this relation. So this is basically what I'm doing here is like I have my graph. I take graph cross 0, 1, and then the way I've written this, I'm gluing top to the bottom. So X comma 1 comes back to the bottom by applying the map F. G, yes. Yes. So this is X. So it will be a two-dimensional complex, finite two-dimensional complex. And And let's just give it some cell structure. So if I look at a 2-cell in this, let's look at the edge E. E has endpoints V and W. And let me call these edges, the vertical edges, which are coming from that 0, 1 direction. Let me call this edge EV, let me call this EW. And 2 cells in this will look like this. So basically I want to subdivide. Okay, I guess I'm giving you a subdivision for this, a cellular structure. So I want to subdivide G cross 1 such that the map so I want to subdivide this. So this is like B, A, B. So I'm subdividing the top such that when I map it to the bottom, like this subsegment maps to B, this subsegment maps to A, this subsegment maps to B, and I like glue it back to the bottom. This is okay. This is what 2 cells will look like. Okay, then what's the let's just write a presentation for the fundamental group of this 2 complex. So that is so these AIs, these are generators of G. So G is a graph, so its fundamental group is a free group, and T is the 0, 1 direction. And these are exactly the 2 cells that I'm attaching. So
So,
yeah. Endomorphism. So yeah, so what I'm doing now, just any graph map will work. I just have to map to non-degenerate edge paths, but otherwise any edge map, yeah, need not be an automorphism for this Alexander polynomial calculation. When we do the Macmillan polynomial stuff, then we start needing things to be better behaved. Okay, so for our example, maybe let's just write down. So if I want to write the fundamental group, I should first write the fundamental group for G. There I have to choose a maximal tree. So let's choose edge F as the maximal tree in G. Then the fundamental group of that graph is generated by, let's say W is the base point. So I have AF inverse, then B inverse F inverse, C F inverse, and so on. So this is AF inverse, B inverse F inverse. And then I have my state. So this T is called stable letter, like the circular direction. That's called stable letter. And then I guess I'm not going to write out the. I should have written G star here because I'm writing fundamental group. Any questions so far? Okay, so I have my X, I have my gamma. Let's look at what H looks like. So H was this guy. And okay, now let K be the image of fundamental group of G in H. So pi1 G sits inside pi1 X, then that's sits inside H. So basically, what am I doing? So I have these generators, and I want to compute the homology of gamma, I just have to abelianize. Like I can start with this presentation and abelianize things. So when I abelianize, what I will get is AI equals to G star AI. So I'll get equations like AI equals some like A1 plus A2 plus A3, stuff like that. And using those equations, I can compute which of these generators end up being trivial in homology and which are non-trivial in homology. So that's pretty easy to do. Okay, so once I did that calculation, I get that some of these generators are non-trivial and others are trivial. So these are non-trivial, and these are trivial in homology of H. So let alpha be the non-trivial homology class. And then I'm saying that K is generated by alpha. And for our example, H is just Z squared. So I'll get one class alpha, and then I'll get the other class from that T, homology class of T. Well, in this example, I have to be careful. Like the vertex V will map to W when I go up, and then I have to like do it twice in some sense to come back to the sake to close the loop. Okay. And then just one more piece of notation. I don't even know when I will use this, but let's write it. Let U naught be the cohomology class or homomorphism to Z such that fundamental group of G maps to 0 and T maps to 1. Sorry, ignore what I said about T is already a stable letter, meaning it's already an element of fundamental group. Okay. So I have homology. Now I want the universal free abelian cover. So I already drew a picture. So let's just check. This okay. So this is the universal free abelian cover. So okay, let G naught tilde to G. Not the universal free abelian cover. Sorry, this is the cover of G with tech group K. So K is not the full homology of G, but it's just the homology as seen in H. Okay, so G that's G naught tilde here. And let's just quickly check. So these elements, they are in the So if I were to write this short exact sequence, this is the fundamental group of that cover. And this DF and EF are in the kernel because they are 0 in K. So at least what picture I'm drawing, let's just check that DF and EF are non-trivial in the fundamental group of this guy. So I have D, F inverse, and I guess for E, EF. So these are non-trivial in the fundamental group. And then let's just see how does AF or alpha act. So maybe since A is here, so A will take W tilde here, and then I see, let's see, this should be some translate of F. This should be labeled F tilde, so it will be A F inverse. So W tilde will end up here. This will be alpha W tilde. So I'm just trying to explain the action of alpha on this guy. So the action of alpha is it like V tilde maps here. I guess it's like shifting by 2 of these circular things, 2 of these data graphs. That's the action of alpha on this guy.
This was not the 10 class for the first one.
No, so yeah. So I first built G naught tilde, which is the cover corresponding to this K. And now I want to build X tilde. Yeah, I've already. So X tilde will basically be this G naught tilde cross I. And I've just like marked these slices of G naught tilde here. That will be the free abelian cover for the mapping torus. So now I want to fix. So eventually I want to write some homology groups, right? And I want to, they will all be like ZH modules or ZK modules. I want to fix a basis once. So my bases are, so basically these red things are my fixed lifts. And using these, I'll write the various CH modules. So I fix the lifts, E tilde, W tilde, fixed lifts of these edges. Okay, now I also fix a lift G tilde. So G was a map from G to G, and I want to look at a lift G tilde from G naught tilde to itself, such that I want to send E tilde to omega tilde. So I'm just making some choices here. They won't matter in the end. Okay. Should we first? So we'll keep that picture. Okay, this is, let's see if I can explain this. So I fix the lift G tilde of my map, and I want to say that this gives us splitting. Of the homology group, which I already knew was Z squared. So I want to understand the action of H on this thing. Such that under the map U naught, which factors through H, alpha maps to 0, and Z, in fact, I am choosing it such that it maps to -1. Or basically my choice of the lift will tell me that it has to map to -1. So maybe I should try to explain. So this Z is acting as a deck transformation on my cover, on this cover, and I'm going to hide this for a second. Z acting as a deck transformation. By translating downwards. So I want, this is the way Z will act. I want Z to, so V tilde goes to Z V tilde. I'm assuming, I'm saying it moves things down, and it's moving it to a vertex such that, so my, this space has a flow direction, which is just if you're standing at a point, just go straight up. So I want, so Z is acting such that when I flow up, I hit the image of V tilde. These are the choices that I'm making, and it's mapping to -1 because the stable letter T that I choose, like I always assume that's going up. So these are, I guess these are some conventions. They are all consistently chosen. So the important thing for us to keep in mind is now I have written H as alpha plus Z, where alpha is like the deck transformation of G naught tilde, and Z is translating down. Okay. It's basically a bunch of algebraic topology that we'll talk when. Okay. Now I want to study the chain complex. So just so that we understand things, I'll write the chain complex for the space X, and I'll write it for X tilde. Then recall my ultimate goal is to write a presentation for X tilde relative to little x tilde. So just so that we are comfortable, I will also do it for X. The whole goal is to write presentation for homology of X tilde relative to little x tilde. And that will come from chain complexes. That's the idea. So we're just doing chain complex for X. So these are, I'm already thinking of these. No, for X, this is just this, sorry. Chain complex for X, let M be the map induced on one chains. So this, if you were in the colloquium talk, this is like this will be a matrix obtained by abelianizing the map G in some sense. So the map induced on one chains, and let this be the, let this be the map induced on vertices. So P here is permutation, basically, because the vertices just get permuted. Okay, the space C naught X, that's just Z to the V, and this space is Z to the E plus Z to the V. How many one cells do I have in X? As many as the horizontal edges. And then how many vertical edges do I have? As many vertices as there were. So like if I were to make the mapping torus for this guy, so I will have 6 horizontal edges. And then since I'm doing this thing cross I, I'll have 2 vertical edges. Okay. So I have my chain complex. This thing is, so for my example, this thing is Z2. This is Z6 plus Z7. And how many 2 cells do I have? I have a 2 cell for each horizontal edge. So this is Z6 in our example. Okay, let's write what this matrix P is. So so P will be, So basically P is the boundary map, and I'm writing a matrix. So I just want to see what's the boundary of HA. HA, the boundary would be V minus W. And so on. I can fill that, whatever this is. For EW, what will be the boundary of EW? So EW, remember, it's the edge starting at W and going to V. So it will be V minus W again. So 1 minus 1, and here it will be minus 1, 1. So this is, this matrix is particularly nice. It's basically this I should have written, this permutation matrix was just this, right? V maps to W and W maps to V. What I'm getting here is P minus identity. And this is something, let's just call it B. This won't play much role. And the map here, M. So for M, I will have two cells corresponding to the A, H, A, H, B, H, so on. And then oh, sorry. Yeah. Okay, what's the boundary of sigma A? So what is sigma A? Do I have?
By the way, I don't know if you will help that much, but there is this thing.
Which thing?
This thing.
Uh-huh.
Yeah.
Oh, okay. What is the boundary of, like, what is the two cell sitting on top of A? WB. And then here I have F of G of A, sorry. Right? So what's the boundary of this two cell? It will be minus E dot, let's just do A plus EV minus G of A minus EW. So this will be, and I'm writing G of A, but I should be writing everything in one chain, as one chain. So I have A minus G of A plus EV minus EW. If I were to be writing everything as one chain, I'm basically, this is I minus M A. The map G acting on one chain is just the matrix M. And then plus, what is this EV minus EW? It's coming from boundary of A, V minus W. So cool. So what does this matrix look like? Here, I just get identity minus M. And then here, I'm basically for A, I'm getting its boundary here. For B, I'm getting its boundary, and that's the same matrix B here. Yeah. What? Okay. So this was just baby case to do. Basically, I'm interested in X tilde, but now that we understand this, it will be easier to understand X tilde. Morally, X tilde is just basically the same things, but as the H modules and nothing else. Let me. So now. Chain complex. Yeah, I guess maybe I will, since I have only 15 minutes and I prepared like an infinite amount, I will do this thing and then I will actually at least tell you the theorem. And then we'll see about the proof. Because after this, I would have at least defined everything that shows up in the theorem. Okay. So before going to X tilde, let's just focus on G naught tilde. Yes.
No, next week is not in. I think I was smart.
I can go the week after, you know. If you are not bored of doing all this like algebraic topology, then sure. Yeah. I mean, I guess there will be some linear algebra later. I don't know. Okay. Okay. So these are ZK modules because K is acting on G naught tilde. And then I have so now I'm calling this matrix P tilde, the map induced on G naught tilde, and let's call this M tilde. And notice that the map. So if I send the map where I send every element K to 1, this map will send M tilde to M and P tilde to P. Okay. So then I want to look at the chain complex of this X tilde now. Okay, so these are all like ZH modules now. So this thing will be isomorphic to ZH to the number of vertices. This will be ZH E plus ZHV, and this would be ZH. And then I want these boundary maps. And I guess I can do the same analysis to try to understand what these boundary maps are. So let me just skip that part and tell you, hopefully should be believable, that these look like so there is this extra Z bar in there, and that's coming from like now that I'm in X tilde, I have that deck transformation Z bar, so that shows up when I do boundaries. The stable letter. Yeah. So I should say, like, at least the first time I was doing an example and computing these maps, I did lots of mistakes with base points and actions, but it's just like doing it. There's nothing more to it. Okay, because I think if I skip this, then I can actually write the presentation. Shouldn't like that. Okay. So recall that we want a presentation for this ZH module, right? That's the goal. Let T be a maximal tree in a one skeleton of X, and let T tilde be its full preimage. Then this Alexander module is actually isomorphic to the relative homology with respect to T tilde. That's just write the long exact sequence for this triple. Okay. Then let E T tilde
Actually, consider some two bunch of vertices, right? So I'm pulling them all.
yes.
And so basically, for every pair of vertices is the limit of the base point. There's also a generator of the homology apart from the generator with external lights and
Mhm.
how is that reflected in the right side? With respect to the the tree.
Yeah.
That's not that's actually the elevation of the all the components.
Yes, it's the full preimage of the maximal tree. T tilde corresponds to a component of X tilde. Yes. Yes. Yes, I'm using this E to denote the set of all edges. And this is the edges not in T. And note that how many edges are not in T? It's exactly these many. So maybe just convince ourselves through this example. The total number of edges is 6 plus 2, 8. The maximal tree will have one edge. I can choose the vertical one, that's it. Then that's 7. So you can do Euler characteristic count of the chapters. Okay, so now finally the chain complex for relative homology. So this guy is just 0 because I'm doing relative to the maximal tree. This guy is as many edges as outside the maximal tree, and this is still the horizontal. So now I have this is number of edges plus 1, horizontal edges plus 1. Okay, so now this is really helpful. Now that this guy is 0, I can use this to write a presentation for the first homology of X tilde, T tilde. So I think I'm going to erase these pictures now. Oh, I have an empty board. So I get because the kernel, because this is 0, the kernel of the boundary map is the whole thing. So I get this presentation. Basically, I have VH E. So I have this presentation matrix. And let's just recall what is this presentation matrix. This is it's this boundary map, boundary 2, and yeah, good, I have that. So I have the boundary map for the whole, like for the actual chain complex. When I'm doing things relative to the maximal tree, I'm basically just throwing out rows corresponding to edges in the maximal tree. Because, so if you recall, this was and so on. So I'll be just throwing out for the boundary map here, I'll be throwing out some horizontal edges. And for what we do, we choose the maximal tree carefully. And we actually want to choose like these, in my example, the edge EW or EV, let's say EV gets cancelled. Like that's my maximal tree in the example. Okay. And this is the GCD of E by E minus of P. So I should write what P is again. And let's say I'm removing that one row. That's how I chose my maximal tree. Let's say I've deleted one row. And what's our theorem? Our theorem is that with Dowdall and Taylor is that this Alexander polynomial is the determinant of this determinant divided by this determinant up to a unit. So maybe for a second, if I ignore this bottom factor, P tilde was basically a permutation matrix. So a particularly simple term. But if I just focus on the top term, I want the GCD of minors of this E by E minors. One of the E by E blocks in my example is already the guy I want. Right? This is what I want the GCD to be. But of course, I have to check all the other minors as well. I have to delete every row and see if I get the same thing or not. So the whole point of like how this theorem is proved is we write this bottom row. If I could write this bottom row as a linear combination of the other rows, then I'll win. Yeah, that's the linear algebra part. So if I could just write this row as a linear combination, I'll be done. But it turns out I can only write a multiple of this row as a linear combination. I can a multiple by some element in ZH. So I have to be a little careful with the determinants because I have a multiple of this row as. So somehow like those, for all the rows, those multiples fall out. And I have to say the GCD of those multiples is 1. Something like that. And this theorem, why were we interested in proving this theorem? Well, A, we wanted to relate it to some other polynomial. And B, this gives us directly, this helps us see that if I look at the map induced on homology for that graph map, its spectral radius. I can directly see that that spectral radius is something called a specialization of this polynomial. Like if it was this, oops, then a specialization is, sorry, this is the last bit is related to the colloquium talk. So U is a cohomology class. So for a given cohomology class, I can find the spectral radius of the map induced on homology. So I'm just using this polynomial. And I will stop here.
Yeah, so this one thing we got the denominator,
I guess this is the permutation matrix. Sorry, I was using P also for the presentation. Let's call this bold. Yes. Yeah, that's the C0 map. This is the C0 map. Yes.
For example, suppose you have a geometric orthogonal service with a function. That's a special case. This must translate to something. And there must be classical algebra formula must have something special. Say, let's say you have a fiber knot. So then you have your encapsulation. Yeah, that's right. So basically, we look at it very common. So this is about and essentially you look like a one graph, which is the skeletal of that. So you have all the stuff about first essentially chain first chains one level back
Right.
and zero level back. Is there something here also where it can actually translate back to the classical case?
So from what I know, so Macmillan directly proved that this polynomial divides the Macmillan Teichmuller polynomial, and I don't think he had a determinant formula for the Alexander polynomial.
So it's fine. So I think that seems to sort of suggest that at least in the very special case of fiber plots, the theorem should give a different expression for Alexander itself should say something about the Alexander polynomial for fiber plots.
I see.
I mean, basically, two manifolds that are
Mhm.
also fiber plots. Then right, because the Z delta is basically your deck translation, right?
Yes,
Right. It's the genetic extension, right?
it's the stable letter, how that's acting on
That's
homology.
the Z.
Yes.
And so you might as well assume that there's a single zero cell.
Mhm. Yeah, like I guess I was trying to do an example where all this would be much easier if I just had like one vertex. Yeah.
Right. So for example, single zero cell, what does this become? It becomes
So this would be identity. So this would just be 1 minus z bar.
exactly.
Yeah.
So okay. So that sounds very neat. Okay, so basically, if you look at a fiber plot, you have the generator with the homology upstairs. You'll be able to look at your Z data, and then it's just divided by 1 minus.
Oh yeah. So okay, you wanted. I see. I should have said this earlier. Like this bottom factor, it turns out to be so like in your fiber manifold or two cell, you'll have some of these vertical cycles.
Yeah.
So it turns out to be a product of those vertical cycles in some sense. So like here, if this was just, there was only one vertex, this would be 1. I would just get 1 minus z bar. And z bar for me is that vertical cycle. So the bottom half is just like the product of 1 minus those vertical cycles.
Yeah, I've seen that. Okay, just have one.
Yeah.
So then I think this looks very good. It's 1 minus Z bar times the other polynomial
Is this determinant?
So
Yes.
this is
Okay.
okay, fair. So this is a, I mean, I was.
You were trying to
there's a standard kind
Ah.
of formula for the polynomial get back and
Yeah. I guess I was saying maybe there is no formula like this in the manifold setting, but I think there is because we use a lemma of Hironaka where she like a lemma where like since I have these scalar multiples of rows, it's like a simple lemma, like, but it helps you deal with that. So I think there is some kind of determinant formula there as well. Thank you. So I guess what was left was just the proof of this theorem. And I don't know if that's still interesting or, I mean, I've told you what goes good.